Hello friends, today we are going to study circular motion, and this is very important topic. It's because there are many applications of circular motion appearing in various areas of physics. So let us start with few basic definitions related to circular motion. So let's consider motion of this particle along circumference of this circle, and suppose it is moving in anti-clockwise direction. So our particle starts at this point P, and in some time delta t, suppose it moves from point P to this point Q, and the angle through which this radius vector moves is suppose delta theta. So this angle is called as the angular displacement of the particle. Now, as the word displacement in this term suggests, it's a vector quantity. So I will put this bar on top of it to show that it's a vector. Now it has magnitude as well as direction, and magnitude is just the magnitude of this angle, and we know that the SI unit for an angle is radians, or RAD in short. To find out direction, we make use of the right hand thumb rule, and right hand thumb rule says take your right hand, curl the fingers of your right hand in direction of motion of the particle, here it is anti-clockwise, and stretch your thumb. So your stretched thumb gives the direction of angular displacement. Okay, so take your right hand, curl fingers in direction of motion of particle, and stretch your thumb. The stretched thumb gives the direction of angular displacement. That's the right hand thumb rule. Then, as we have defined the displacement, just like the case of linear motion where we have velocity equals to displacement divided by time, here we can define a quantity called angular velocity. We denote it by this letter omega. It looks like W. This is called omega. So angular velocity is angular displacement divided by time. So it is delta theta over delta t. Now here we did not consider how fast or slow this particle moved. So this is in fact the average value of angular velocity. Okay, so this is average angular velocity. Then in order to find the instantaneous value of the angular velocity, we need to take derivative of this theta with respect to t. So let me write instantaneous angular velocity is d theta over dt. Okay, then if we have change in angular velocity, then we will have a quantity called angular acceleration. Just like linear case where acceleration is change in velocity divided by time, we can define the angular acceleration for this particle performing circular motion So angular acceleration is denoted by this letter alpha, and this alpha is change in angular velocity over time. So suppose omega naught is the starting angular velocity at time t naught, and omega t is angular velocity at some time t, then we can find alpha equal to change in angular velocity, which will be omega at time t minus omega at start. Omega at t naught is omega naught divided by t minus t naught. Okay, so this is again the average value. In order to find the instantaneous value, the instantaneous angular acceleration, alpha will be just derivative of omega with respect to t. Circular motion can be categorized into two types: uniform circular motion and non-uniform circular motion. Now, uniform circular motion is quite obviously circular motion with constant speed or uniform speed. So suppose now our particle is performing uniform circular motion, or UCM in short. So let's try to find out expressions for few quantities for this particle which is performing UCM, and we'll start with the speed of the particle, which remains uniform. So we know that the speed is distance covered divided by time taken, and suppose capital T is the time taken by this particle to complete one revolution along this circle. So this time is called as time period, or the periodic time for this particle. So let's denote speed by v, and let's take time equals to the time period. So distance covered in this much time period would be equal to the circumference of the circle, and that is 2 pi r. So we found expression for speed of the particle performing uniform circular motion, and that expression is v is equal to 2 pi r divided by the time period. Then suppose n is the frequency for this particle. So frequency is number of revolutions performed per unit time, and therefore n is equal to unit time divided by time for one revolution, and in SI units we take unit time as 1 second. So it is 1 divided by time for one revolution is the time period. That's why frequency is 1 over t. And the unit is revolutions per second, okay, or it is also called as hertz. Now using this formula for 1 over t is equal to n, we can substitute that here and we can find out that speed is equal to 2 pi r multiplied by 1 over t, and 1 over t is n. So formula for speed is 2 pi r multiplied by n. Okay. Then let's find out the angular speed for this particle. Angular speed is the magnitude of angular velocity, and we know that angular speed is denoted by omega, and it is delta theta, the angle covered, divided by time taken. So if we take time taken equals to this capital T, the time period, then what would be the angle covered? So angle covered would be equal to 360 degrees or 2 pi in radians. So omega is 2 pi divided by t, and since 1 over t is n, we can write that omega in terms of n is 2 pi multiplied by n. Then let's relate the linear speed of the particle and the angular speed. So the relation between linear speed and the angular speed. So we know that linear speed v is equal to 2 pi r divided by t, and in place of this 2 pi over t, I can substitute this omega. So substituting that, what I get is v is equal to omega times r. So it is linear speed of the particle is equal to angular speed of the particle multiplied by the radius of the circle. So this is the linear speed and the angular speed of particle performing uniform circular motion. Now let's check whether there is some acceleration in uniform circular motion. So one might ask, if speed of the particle in UCM remains constant, why should there be any acceleration in uniform circular motion? Answer to that is, we define the acceleration as change in velocity over time, and we know that the velocity is a vector quantity. So there can be change in velocity if there is change in magnitude of velocity, or even if there is change in direction of the velocity. And in uniform circular motion, the magnitude of velocity, which is speed, remains constant at each and every point, but the direction of velocity, which is tangential to the path of particle, it keeps on changing. So that's why we have change in velocity, and that's why we have acceleration in uniform circular motion. Okay, and its direction is radial. It is along the radius and directed towards the center. So it is called as centripetal acceleration. So our job now is to find out the magnitude and prove that the direction is towards the center. So suppose the velocity of particle at point P is Vp bar, and in some time delta t, the particle moves from point P to this point Q, and velocity there will be tangential at that point. But since speed remains constant, the magnitude of velocity will be same, and therefore length of this vector will be same as that of length of this vector. So this is VQ bar, and suppose this angle is delta theta. Okay, so to find out the acceleration, we need to find out the change in velocity, and suppose change in velocity delta V is VQ bar minus VP bar. To find out the change in velocity, I will take VP bar here. So that's my VP bar, and you can convince yourself that change in velocity will be directed like this. This is delta V bar. Since we can say VP bar plus delta V bar is equal to VQ bar, using the triangle law of vectors addition, and we can take VP bar on other side, and we have delta V bar, which is VQ bar minus VP bar, represented by this vector. Okay, then since this angle is delta theta, this angle also will be delta theta. It's because this is angle between radius at time t equal to 0 and radius at time t equals to delta t, and we know that the velocity is tangential, that means it is perpendicular to the radius. So if angle between two lines is delta theta, then angle between perpendiculars drawn to those two lines should also be delta theta. Since both lines rotated by 90 degree will give us perpendiculars, and if we rotate two lines by 90 degrees, then angle between them will not change. So those two angles are same, and if I join this PQ, so this is R, let's say this is RP bar, position vector at start, and this is RQ bar, the position vector at some time delta t. So this side PQ will give me the change in position vector. Okay, so this side will give me delta R bar. Now I will redraw these two triangles here. And then we know that the length of VP bar is equal to length of VQ bar, since the speed is constant. So we can say magnitude of VP bar is equal to magnitude of VQ bar, and that is equal to, suppose, V. So for this triangle, we have length of this side equal to length of this side, and it is V. Angle between those two sides is delta theta. And for this triangle, we have length of this side equal to length of this side, since those are radii. Okay, radius at some time and radius at some later time. So this angle is also delta theta. So we can say that these two triangles are similar, since we have two sides of equal length and angle between them is delta theta here. Here also we have two sides of equal length and angle between them is also delta theta. Now we can use the property of similar triangle. So I can say, using property of similar triangles, if I take ratio of this side to this side, which is length of this side delta V over V, it should be equal to the ratio of length of this side to length of this side. Okay. So ratio of lengths of corresponding sides is same. Now I will take V on other side. So I can rewrite this as delta V is equal to, I will write this as delta R multiplied by V taken on other side. So that V divided by this R. And now our job is almost done. So we can divide both sides by delta t and take limit as delta t tends to 0 to find out acceleration. Okay. So dividing by delta t and applying limit delta t tends to 0, we can rewrite this. Okay, for that let me erase this part. So limit delta t tends to 0, delta v by delta t is equal to, here limit delta t tends to 0, delta r by delta t multiplied by v over r. Now this limit delta t tends to 0, change in v or change in t will give us acceleration. That's the acceleration we wanted, and we'll prove that it is directed along radius and towards the center. So I will put this suffix for centripetal acceleration, and it is equal to, on right hand side we have this limit delta t tends to 0, the change in position with respect to time, that's velocity. Okay, so actually it's the magnitude of velocity, so it is v divided by r, we have v by r. So acceleration, the centripetal acceleration has magnitude v square over r. Then now we can substitute for this v omega times r and rewrite this formula as AC equals to omega times r multiplied by v over r, and this r and r gets cancelled. So we have this another formula, AC equals to omega times v for centripetal acceleration, and again I can substitute v equals to omega times r for this v also, and using that I get this another formula as AC equals to omega square multiplied by r. So we have found the magnitude of centripetal acceleration. Now let's try to find out the direction. Okay, let's prove that the direction is really along the radius and towards the center. Okay, now let's think this way. In projectile motion, we had path of projectile like this, and acceleration, which was acceleration due to gravity, was directed vertically downwards. Okay. Now if I rotate this by 90 degrees, I will get path like this, and the acceleration would be directed like this. Again, if you rotate by 90 degrees, you will get path like this, and acceleration would be directed like this upwards. And if we again rotate it by 90 degrees, then the path will look like this, and the acceleration would be directed like this. So we can compare this with the circular motion. So let's compare this part of curve. So for this part of curve, the acceleration will be directed like this. For this part of the curve, it will be directed like this. For this part, it will be directed like this, and for this part it will be directed like this. So you can see, you can imagine that it is directed along the radius and it is pointing towards the center. Okay, so this is the symmetry argument. Now let us argue in some other way also. So let's consider, let's suppose that the acceleration is not directed along the radius and towards center, it is directed in some other direction. So suppose the acceleration is something like this. Now I can resolve it in two components. So this is the radial component and this one would be the tangential component. Now we have uniform circular motion. That means the magnitude of velocity is not changing. But here you are having tangential component of acceleration which will change the magnitude of velocity. Since velocity is directed in tangential direction, tangential acceleration will change the magnitude of velocity, okay, which we don't have in uniform circular motion. Uniform circular motion has constant speed, so we cannot have the change in velocity in tangential direction. So we are left with only one component of acceleration, and which is in fact radial. Okay, and that's why we call it radial acceleration or the centripetal acceleration, since it is directed along the radius and towards the center of the circle. So we can rewrite these formulae in vector form. So in vector form, the centripetal acceleration can be written like this: v square over r along r cap. R cap is the radius vector, but it will be directed outwards, and since acceleration is inverse, okay, it is directed towards the center, it is in opposite direction of the radius vector, and this minus sign shows the same thing. Okay, similarly this formula can be written like minus of omega square into, we can write this r bar here. Okay, and this formula, it needs further explanation actually, but it is omega bar cross v bar. So these are the formulae for the centripetal acceleration in uniform circular motion. Okay, so we have seen that we cannot have this tangential component of acceleration in uniform circular motion, but in non-uniform circular motion there is no such restriction. So we will have both these components of acceleration, and therefore in non-uniform circular motion we can say the total acceleration is a bar equals to ar bar plus at bar. Ar bar is radial acceleration, or let's write ac bar only, and the magnitude of total acceleration will be just given by square root of ac square, centripetal acceleration square, plus tangential acceleration square. So this is the total acceleration if the circular motion is non-uniform. Okay, so now we are familiar with various quantities in circular motion. Next time we'll see some problems on circular motion and motion in a plane. Thanks for watching.